Okay, let's dive right into this explainer. We're going to illuminate a topic, literally, that you probably use every single day but rarely think twice about. We're talking about the surprisingly dramatic history, the intense physics, and yeah, the actual corporate conspiracies behind the light bulb.
We're starting right out of the gate with a massive historical misconception. If you ask almost anyone who invented the light bulb, they're going to instantly say Thomas Edison. But the truth is a whole lot more fascinating. It really centers on a fierce clash of titans, specifically an intense competition between Edison and a guy named Joseph Swan, not to mention at least 20 other inventors who were tinkering with early designs way before Edison even filed his famous patent.
Now, this is where the real story heats up. It pits Edison's sheer commercial genius directly against Joseph Swan, who was a brilliant British chemist. Swan had actually been working on this exact problem since 1850. He took a strictly chemical approach. He finally achieved this major breakthrough using carbonized paper and cotton thread inside a stable vacuum tube, proving a long-lasting bulb was absolutely possible. Edison, though, he was the ultimate businessman. He wasn't necessarily first to the science, but he was absolutely determined to find the most commercially viable solution. The guy literally tested thousands of materials before discovering that carbonized bamboo lasted over 1,200 hours. Talk about a rivalry.
Just look at how quickly this race accelerates. By 1878, Swan was already out there demonstrating his working lamp publicly in England. The very next year, 1879, both Swan and Edison filed patents for highly similar designs. So similar, in fact, that Swan actually sued Edison for copyright infringement in the British courts. And guess what? Swan won. The court literally forced these two fierce competitors to merge their operations in Britain into one single entity, the aptly named Edison Company. So while Edison gets most of the glory today, it was actually Swan's invention of the extruded cellulose rod that eventually became the global standard.
Moving on to Section 1, the physics of the glow.
So, what were Edison and Swan actually trying to achieve inside that delicate little glass envelope? Well, how does electricity actually turn into light? The magic word here is incandescence. When you push an electric current through a resistor, like a filament, it generates a massive amount of heat. This electrical resistive heating excites the atoms within the solid, and to relieve that excited state, the atoms emit photons. But here's the catch. To actually emit visible light, a solid has to be heated red hot to over 850 Kelvin. That's over 1,000 degrees Fahrenheit. And even at those extreme temperatures, only a tiny, tiny fraction of that radiated energy actually becomes visible light. The vast majority of it, totally wasted as invisible infrared heat. It made early light bulbs notoriously inefficient.
But you got to appreciate the staggering engineering required to make a modern incandescent bulb work. Check this out. This is a coiled tungsten filament, magnified 500 times. We use tungsten because it has the highest known melting temperature of literally any pure metal. This tiny, intricate piece of metal is designed to sustain an enormous 3,000 Kelvin temperature. We're talking 5,000 degrees Fahrenheit without melting into a puddle. Think about that. It's probably the hottest phenomenon you will ever closely encounter in your everyday life.
But sitting at 3,000 Kelvin definitely has a cost. Over time, those tungsten atoms actually evaporate right off the surface of the filament. As the tungsten evaporates, the metal thins out. This creates these localized hotspots with even higher electrical resistance, which, you guessed it, generates even more heat, causing even faster evaporation. It's a rapid thermal runaway cycle. Eventually, the filament gets so unbelievably thin that it just snaps. And since a cold filament has about 10 times the electrical current rushing through it as a hot one, this snap almost always happens in that very first super stressful second you flick the light switch on.
Which brings us to Section 2, cartels and planned obsolescence. Okay, so we know filaments naturally burn out over time because of physics. But what if a bulb was intentionally designed to fail faster, specifically to force you to buy more of them? Look at this massive contrast here. On one side, we have a strict cartel-mandated 1,000-hour limit for a light bulb's lifespan. And on the other side, the staggering 1,000,000-hour lifespan of a single bulb that is somehow still burning today. How is a discrepancy like that even possible?
Well, let me introduce you to the Centennial bulb. This is a handmade carbon filament bulb manufactured by the Shelby Electric Company. It was installed in a fire station in Livermore, California, way back in 1901. And it has been burning almost continuously ever since. Wow! Originally a 60-watt bulb, it's dimmed down to about 4 watts today.
But this incredible survivor proves beyond a shadow of a doubt that extremely long-lasting bulbs were entirely technologically possible over a century ago.
So, why don't you have centennial bulbs in your house? 2 words: Phoebus cartel. Back in the 1920s and 30s, this massive cartel took absolute control over the incandescent light bulb markets across Europe and North America. They actually colluded to slash the life expectancy of bulbs from 2,500 hours all the way down to a strictly enforced 1,000 hours. They engineered planned obsolescence specifically to triple their own sales. The cartel took shortening lifespans just as seriously as earlier inventors took lengthening them. This unchecked corporate greed ran wild until the aftermath of World War II, when a U.S. District Court finally found General Electric in violation of the Sherman Antitrust Act in 1950, and the cartel was forced to disband.
All right, let's jump to Section 3, the LED revolution.
Thankfully, modern physics finally provided an escape hatch from that whole era of planned obsolescence and super inefficient heat generation. Enter Nick Holoniak, Jr. In 1962, while he was consulting at General Electric's lab in Syracuse, Holoniak took a totally different approach. While other scientists were playing around with invisible infrared devices, he created a new alloy of gallium arsenide phosphide to emit visible red light. He had just invented the very first practical visible spectrum light-emitting diode, and even back then, he boldly predicted that this exact technology would one day replace incandescent bulbs completely.
Now, Holoniak's invention was a real game changer because it bypassed the heat problem entirely using a completely different physical mechanism, electroluminescence. Unlike incandescence, which relies on generating massive, wasteful heat to excite atoms, electroluminescence relies on radiative recombination between electrons and electron holes within a semiconductor. Okay, in simpler terms, when an electric current is applied, electrons jump to higher energy levels and then drop back down, releasing that excess energy directly as pure light. It gives us this thin, uniform, and highly energy-efficient illumination right from electronic excitation. It completely skips the 3,000-degree middleman.
And the data here brilliantly illustrates the modern victory of this technology. LEDs absolutely annihilate both compact fluorescence, or CFLs, and traditional incandescence. Look at the annual operating cost of running 30 bulbs a year. Incandescents cost over $328. CFLs dropped that to $76, sure, but they rely on highly toxic mercury to function, which makes them a huge environmental hazard if they break. LEDs? They dropped that annual cost all the way down to just $32, and they contain zero toxic mercury, making them fully safe and RoHS compliant.
And honestly, perhaps most importantly, they strike a massive blow against the legacy of that Phoebus cartel. LEDs are rated to last anywhere from 25,000 to 50,000 hours. They really represent the first mass consumer product of the 21st century to truly challenge planned obsolescence, bringing us right back to that built-to-last mentality that the creators of the Centennial bulb had over a century ago.
Finally, Section 4. The future is OLED.
But as we know, technology never stops advancing. The next big leap is already transforming how we interact with light in our homes and businesses. While traditional LEDs are an incredible step forward, they're typically pretty small, intensely bright, and highly directional, meaning they can sometimes cause a pretty harsh glare. Enter organic LEDs, or OLEDs. They function similarly, but they can be manufactured into flat, flexible panels. So, instead of a tiny blinding point of light, an OLED panel provides this beautifully diffused ambient light that spreads evenly across entire rooms. Just imagine a ceiling, or even a curved wall, that itself just softly glows for up to 40,000 hours.
It truly leaves you wondering, doesn't it? As we finally defeat the corporate greed of planned obsolescence and move into an era where we can turn almost any flexible surface into a canvas of highly efficient light, what incredible shadow-breaking technology is waiting just around the corner? From Edison and Swan's intense rivalry over a burning vacuum, to global cartels to glowing walls, what will the lighting explainer look like 100 years from now? Keep questioning the things you use every day, and I'll see you in the next explainer.